Alright, welcome to lesson 7.10. We're going to continue applying our understanding of integrals and antiderivatives to solve rigorous real-world AP style problems. Let's get started. Alright, so we're going to go a little deeper into the process that we've been discussing over the past couple of lessons about how to apply integration to solving some real-world situations. So there's a lot of writing here. You don't want to write all of this down. Briefly write out the important pieces to the question, and then split your paper up in half and follow these steps on the left and then these steps on the right. You don't need to write down each of the steps, just actually do them. Alright, so to start off with, we want to write an integral that will represent the displacement of my particle over the first 5 seconds. And so I remember that displacement is just the area underneath the velocity curve between, in this case, 0 and 5. And so my integral will be the integral from 0 to 5 of v of t dt. And of course, I can write this as the integral from 0 to 5 of cosine of pi t dt. But since I'm not evaluating it, this is perfectly fine. Okay, for part B, I'm writing a function that represents the position of the particle at any time t. And so I remember the two components that go into this. Of course, there's the initial position, so I'll call this s of 0, plus the displacement between the time 0 and whatever the time t is. So this will be the integral from 0 to t of my velocity function, and I need to use a different dummy variable here, so I'll use x. Okay, and now in part C, I'm going to actually evaluate this integral over here so that I can write my function in a little bit easier to work with way. So to do that, I'm going to go ahead and evaluate the integral from 0 to t of cosine of pi x dx. Here I need the antiderivative. We've actually found this in a previous lesson. So the antiderivative here is going to be sine of pi x. And I notice, of course, when I take the derivative of this function, I'll end up with pi out front because of the derivative of the inside. So I need to divide by pi since I don't have a pi out front in this function. And I'm going to evaluate at 0 and at t and take the difference there. And since sine of 0 is just 0, I will just simply have sine of pi t over pi. Now, I know that s of 0 is the position of my particle at t equals 0, and this, of course, is 5. So this allows me to write my position function as 5 plus sine of pi t over pi. Right? And this is wonderful because now I can find the position at any time t. Alright, on the other side, I'm going to use the indefinite integral to take the general antiderivative of my velocity function. And similarly to what I have just discussed in the other side is that the antiderivative of cosine of pi t is going to have the first component, which is just going to be sine of pi t over pi plus any constant c. And I want to set this equal to s of t. So in other words, I'm calling my position function the antiderivative of velocity, which should make perfect sense. And so this is s of t. Now notice that I don't quite have a completed function for position because of the c constant. I don't know what that is, but I can solve for it because I happen to know what s of 0 is. So I will set t equal to 0, and s of 0 will be equal to sine of 0 over pi plus c. I know that s of 0 is 5, sine of 0 is 0, so I end up with 5 being equal to c. And this means that I now have my function, s of t. So s of t is, and I go back to what I had before, sine of pi t over pi plus c, which is now, of course, 5. And so I can write it back in this form. I can put 5 first, 5 plus sine of pi t over pi. So both processes get us to the same position function, as they should, and this means that both processes will work. However, there are differences between the two which might lead one to being more useful in certain situations than the other. So let's take a look at the first process here, and I really like this one because it allows us to write a position function very quickly, right? It's very simple. The position of a particle is determined by the initial position plus the displacement from the initial time to that time that you want the position at. And so this here is a fully formed function. What I mean by that is that you want to use your functions, right? And so you can use this function. You can insert some time for t. You know what the initial position is. And then this is just the definite integral from 0 to whatever your t value is. And so even if you can't take this definite integral by hand, there's ways to do it with your calculator. This will tell you how to, what definite integral you need to do in order to, complete your process for finding the position. And so it's notable that you can write, a fully formed position function without actually taking the definite integral. Okay? This is a perfectly fine function. That doesn't mean that this isn't true. It is true that, position is the antiderivative of velocity, but you can't exactly evaluate this expression here, right? This is an antiderivative. It isn't a definite integral. And so while I can eventually get to a fully formed function here, it isn't the case that at this initial step I have a fully formed function that is going to be useful to me. And so if I am in the situation where I can take the antiderivative here, this process is fine. It might actually be quicker. I just have to find the antiderivative and then use my initial condition to solve for c. However, if I can't find the antiderivative or I can't find it easily, this process here is going to actually be harder. And this process over here will allow me to write a position function in terms of the definite integral. And there will be times on the AP test where they will actually ask you to write a function in terms of an integral. And so when they say that, they're referring to this simple construct here. And so you want to be sure that you can employ it. All right, so with this in mind, I now want to take a step back so that we can look at the relationship between position, velocity, and acceleration sort of in its full glory. All right, so now that we have discussed differentiation and integration or anti-differentiation, we can now come full circle to thinking about position, velocity, acceleration, and moving in between the three functions here. So first, moving from left to right. If I have a position function, I can then find the velocity function by differentiating. All right, so notice, of course, that the derivative of s of t is s prime of t, which is the velocity, the rate at which the position is changing at any time t. And from velocity, I can go to acceleration. Again, by taking the derivative of velocity, I will get acceleration, right? V prime of t is a of t, which is, of course, s double prime. So taking the derivative twice of my position function gets me to velocity. And so this tells me that the process of differentiation, right, or finding the instantaneous rate of change, allows me to move from position to velocity to acceleration. And so I can then move back from right to left using the inverse operation of differentiation, or anti-differentiation. So let's begin by moving from acceleration to velocity. We will anti-differentiate. And similarly, I can then also move from a velocity function by anti-differentiating velocity, and I will end up with a position function. Now, remember, for differentiation, I'm just going to write our operator here. Derivative, in this case, with respect to t, right? That's what I'm doing here. And with anti-differentiation, taking the antiderivative, remember our symbol for that is the indefinite integral, which is telling us the general form of the function, right? We'd have to solve for c to find the specific function for a given situation, but we can represent the general form. So what we can say is that position is the indefinite integral of velocity. In other words, given a velocity function, I can take the antiderivative of it, and that will give me the general form of a position function with that velocity. And then, of course, I can, solve for c if needed. So the same is true. I know that the velocity is the antiderivative of acceleration, and I can represent that using the indefinite integral. So velocity is the indefinite integral of acceleration, which is written as such. And of course, remember, this is going to give me the family of antiderivatives. So if I wanted to solve for a specific velocity function, I would need to solve for that constant c here. And we just kind of discussed that, right, in the previous example. But notice here that we've accomplished quite a bit at this point, right? We can move between position, velocity, and acceleration and back, and that's quite an accomplishment. But we shouldn't lose sight of the fact that we've actually discovered something much more powerful than just position, velocity, and acceleration. What we've really discovered is a relationship between a function which measures an amount, the rate at which that amount is changing, and the function that represents the rate at which that rate is changing. And so it's important to keep the fact that we can apply this to more than just position, velocity, and acceleration in mind, because in life and on the AP test, there will be plenty of situations where we'll want to do this. So again, I'm going to put this up here because it's super important to remember that in general, the definite integral and the fundamental theorem of calculus allows us to apply integration in real-life contexts in this way. The definite integral of the rate of change of a quantity, f prime, over an interval from a to b, is the change of the quantity over that interval, meaning f of b minus f of a. And this is simply the fundamental theorem of calculus, right? Because f is the antiderivative of f prime. And extending this, we can now say we can write a function for f using either the definite integral or the indefinite integral. And so here I have illustrated the method that we used on the left using the definite integral, right? The initial value plus the displacement between that initial value and any time t, and the indefinite integral. But there are a couple of things we need to note for each of these. First and foremost, when using the indefinite integral, I'm then going to need to solve for c using my initial value or my initial condition. Over here, I want to note that this, of course, is a fully formed function that I can evaluate, not too hard to do so, but that if I wanted to, I can evaluate the definite integral, which will give me a potentially easier form of my function to use, the same form I would get if I were to find the antiderivative and solve for c using the initial condition. And so now, whether we're talking about position, velocity, and acceleration, or about the number of gallons of oil that is leaking into the ocean somewhere, we are well equipped to analyze it using the integral. Okay, so there's one more concept that I think is important for us to see before we start tackling some of these trickier problems. So let's go ahead and discover that quickly, and then we can move on to some problems. All right, so let's go ahead and work through this problem. The setup is the same as what we've seen previously. I've simply graphed over here the velocity function, and so you'll want to spend some time copying this down fairly accurately. And of course, don't worry about writing these out word for word. We just want to go through this and discover something. So work through it and see what you discover, and then we'll take a look at it together quickly. So the first part is pretty simple here. I just want the displacement of the particle over the first 3 units of time here. And so I'm just going to take the definite integral from 0 to 3 of my velocity function. And what I end up with is 0, which seems a little interesting, but remember, we've seen this before. The displacement of 0 just means that my particle is in the same position at t equals 3 that it was at t equals 0. Okay? But we want to dig a little deeper because 0 seems like a weird thing to get. So let's use the signed areas underneath the curve to justify why you got a displacement of 0. So let's look at the area underneath the curve up until t equals 3. All right, so notice that there are areas in green and areas in orangish pink. And the areas in green represent, of course, area above the curve, which we interpret as positive value area. And this area here is going to be area below the curve, which we interpret as negative valued area. And the reason this is that in this particular situation, when we have a negative velocity, we want to represent that we are traveling to the left. Whereas with positive velocity, we're going to be traveling to the right. And so what you'll notice is this area represents an amount traveled to the right, and that's the same as this area, which represents traveling to the left. So these two are going to cancel each other out. This movement to the right is the same as this movement to the left. Similarly, this area represents a movement to the left, and this area represents a movement to the right, and they have the same area, so they represent the same movement just in different directions. Well, since the area that represents movement to the right is the same as the area that represents movement to the left, it makes sense that after 3 seconds, we're in the same place. However, is it correct to say that the total distance traveled by the particle in those first 3 units of time is 0? Well, think about this for a second. Just because I'm saying the displacement is 0 doesn't mean that my particle didn't travel at all, does it? No, certainly not. It travels to the right, travels to the left, it travels to the right, it travels to the left. So it's traveling a bunch. It just happens to be that at that instant t equals 3, it's back in the same place it was at t equals 0. So how can we find the total distance? Well, notice that total distance is just going to be a positive number. There's no negative values involved in total distance. In other words, what we want to do is count the distance traveled to the left as a positive value, and the distance traveled to the right as a positive value, and we want to add all those positive values up. So it's easy to say, okay, well, let's just find the area here. But remember, we're using the integral. So within our integral, how can we make sure that our integral counts this distance traveled and adds on this distance traveled instead of subtracting the two and finding, the displacement? Well, that's actually a lot simpler than you might think. Remember we talked about absolute value? Well, imagine if you evaluated this as the absolute value. Well, whenever you take absolute value, whatever was negative becomes positive. So let's quickly look at what the absolute value of velocity looks like as a graph. So notice, of course, when we graph the absolute value of velocity, all of the areas are now above the x-axis. So when I now take the definite integral from 0 to 3, it will actually be computing the total distance. So here, these integrals here are going to compute the total distance. The question now, of course, is how do I actually compute this value here? This is actually a much easier problem than you might imagine. Notice that all we've done is take the areas beneath the x-axis and turn them positive. So all we need to do is integrate, instead of from 0 to 3, we need to integrate from 0 to where the function stops being positive and goes negative, And then we need to integrate from where it goes negative to where it then returns to being positive. So we'll have a definite integral that represents this area. And then, of course, we take the definite integral from this point where it goes positive to where it stops going positive. That'll give us this area here. And then we take the definite integral from here to here. And that will allow us to, with these definite integrals, when I take the definite integral from here to here, I can turn that value positive quite easily. I can take the absolute value of it. I can multiply by a negative. In fact, notice that this function here, absolute value of v of t, between these 2 points, I can get this graph exactly by multiplying this function here by a negative. In other words, multiplying cosine of pi t by a negative when I'm computing the integral between these 2 points and between these 2 points. And so there's multiple ways. The big picture is that I want to treat this area here, which normally is computed as a negative area, as a positive, so that I'm continually accumulating total distance as opposed to getting displacement, which counts them as a directional notion. All right, so let's go ahead and write down the definition for total distance. You may want to remind yourself what displacement is. We've discussed that previously. But in contrast to total distance, it's very similar but has one minor difference. The total distance traveled on the interval from t sub 1 to t sub 2 can be found by integrating the absolute value of v of t, also known as the speed. This will calculate all area as positive area. So total distance, of course, is always going to be positive, whereas displacement can be positive or negative depending on the positional change. So the one minor question here is to make sure that we have a clear understanding of how we can integrate absolute value of v of t by hand. If we did this with our calculator, we could just enter the function in absolute value brackets and it would do that for us. But when we don't have that option, what we need to do is envision the graph that we have on the previous slide there, and remember that all we need to do is when v of t is negative, we need to turn it positive so that we end up with a positive area. And the easiest way to turn a negative value positive is to multiply it by a negative. So what we're going to do is when v of t is positive, we just integrate as normal. But when v of t is negative on that interval, we'll integrate negative v of t so that we end up with a positive area. And this is actually quite simple. The only work that we really have to do here is find out where v is negative and where v is positive. And we can do that just, you can make a quick little sign chart, and that will help you ascertain that information. So let's go ahead and do a quick example with that, just to make sure we feel comfortable finding total distance. Now let's use the same example we've been working with so far to compute the total distance traveled by the particle between t equals 0 and t equals 2. So just looking here, you can see that the displacement between t equals 0 and t equals 2 should be 0. The amount of area above the t-axis and below the t-axis is the same. So when we're finding the total distance, we're going to need to make sure that we locate these points between which the function is negative so that we can integrate negative v of t over this interval, and then we can integrate positive v of t over these two intervals here. So let's go ahead and set our velocity function equal to 0 to solve, make a quick little sign chart, and then we'll be off with our integration. Alright, so to do this, I'm going to set v of t equal to 0, which boils down to when cosine of pi t equals 0. And I can solve this using inverse cosine if I'd like, but either way I'm going to need to go to my unit circle here to do this by hand. And remember, cosine is 0 at pi over 2. And so think about what t would have to be so that I get pi over 2 in here. It just have to be 1/2. And then, so that works nicely. And then it's also going to be 0 here at 3 pi over 2. Right? 1 pi over 2, 2 pi over 2, 3 pi over 2. And so if I want to get pi times t to be 3 pi over 2, I need t to be 3 over 2. And I can see these match up nicely. 1/2 and 3 over 2, which is 1.5. These are going to be the 2 points, t values, at which my velocity changes from negative to positive. And I can make a quick sign chart here. So let's go ahead and show the solution. This is when t is equal to 1/2 and 3/2, or 1.5. And if I make a quick sign chart for my velocity, I can plug in a couple values in between here, or I can just look at the graph. That can save us a little bit of time. It's positive, negative, and positive. And so on this interval from 1/2 to 3/2, I'm going to integrate negative v of t, because v of t is negative here, so when I multiply by a negative, it will turn into a positive function, which will allow me to get a positive area. So setting up my integral will look like this. I want to show the integral that I'm integrating that will give me the definition of total distance, the absolute value of velocity. And then I'm going to show that I've broken it up into the intervals where v is positive, so I'm integrating just v of t, and then where v is negative, so I'm integrating negative v of t. And by now you should be a pro at evaluating these integrals. To check your work, each one of these, so this will be 1 over pi, this will end up being a positive 2 over pi, and this will be another 1 over pi, which leaves you with a value of 4 over pi. And so that is the total distance that you've traveled between time 0 and time 2, 4 over pi units. And you could make a nice approximation here, recognizing that pi is pretty close to 3. So it's going to be pretty close to 1 1/3, and it works out to approximately 1.2732. And this makes a lot more sense for total distance than just using displacement, whereas the displacement between 0 and 2 ended up being a displacement of 0. We recognize that total distance will monitor the distance that the particle is traveling, so it will count even when it's moving to the left as a positive component of the total distance. Okay, at this point it's worthwhile to discuss the general form that most AP free response questions are going to take, particularly when they involve you doing a good amount of integration, definite integration. And this is really helpful because it allows you to know what you're expecting, and a lot of time that's half the battle when you're taking a test that's this rigorous. So this follows the basic format that you would follow if you were just trying to analyze some information or some data in real life. So given some information about a situation or some data, you want to first make an approximation. So there are a couple ways that we've done this. One is by finding the average rate of change. That was way back in semester 1. And of course, with integration, we can approximate the area under the curve, or what that represents now in a real-world context, using a Riemann sum. Approximation. And of course, we have multiple ways that we can do this, a left endpoint, right endpoint, midpoint, or even a trapezoidal. Now, once we've made an approximation, we want to actually calculate the exact value. So what we'll do is we'll write an expression to calculate the exact value that we just approximated. So if we were approximating a rate of change, we would now take the derivative, right? Just represent it like that. If we want to find the exact value of our Riemann sum approximation, well, we know as the limit as n approaches infinity gives us the definite integral. So we want to integrate, set up an integral. And this will take different forms. Maybe we actually are writing a function for position, or maybe you're writing a function for velocity or acceleration or something like that. But the basic idea is that now we're actually going to try and set up something that will calculate the exact value. And so then, and I might mention here that this could be probably be a definite integral. And so now we want to actually use our construction from part B to find the exact value. So whether we found a derivative or we integrated, we'll now be able to calculate what we approximated originally. And it's not always going to be the case that these are broken up into A, B, and C. They might combine these steps into two parts of a question. And then from then on out, you can sort of extend your reasoning. You can introduce some new situation, or some new thing pops up, you're comparing to something else, and so you're going to kind of work off what you've already found to make some more comparisons, extend your reasoning. And notice here, if you look at this right side, this really follows in line with what we've done this unit, right? We looked at area under a curve, what that can represent. We found some approximations using Riemann sums. We then developed